My name is Dengteng Ge from the Donghua University, China. So today I will introduce my works about the bio-inspired dynamic surface and interface for optics and wettability. So before my presentation, I will introduce our university first. So Donghua University is in Shanghai. We have two campuses. One is in the central city. They just do the fashion and the design for the fabrics and clothes. Another part is in the Songjiang. So we just do the science and engineering for the fabrics and the materials. So in our group, we just called the Dynamic Tech Lab for the bionic material and the structure. We are interested about the bionic material and the micro pattern. So we use the cradle pattern. Hope that this material can be used for the optics, thermal, and the wettability. So another part is we just do the functionalize the thermoplastic composite. We hope these two kinds of material can be used for the robot. So like the functional skin on the composite skeleton. So we just want to do the dress for robot. So now just let us start from the butterfly wings. People are interested about the butterfly because they are shining colors. So here there's two kinds of butterfly. The left wing is the color is from the pigment, and the right wing is from the structure. This one is a morpho butterfly. It's very shining. So I list another structure color in the butterfly. They also have the iridescent structure color like morpho and others, and also the white, ultra white, and the metallic white, and the racial reflection. In the recent years, we also found a special species butterfly they call the custodians. They combine the metallic white with the and the racial reflection. So you can see the white spot, shining white spot as particular angles. And on the other angles, you can see the spots. This white, we can find the color is from the color mixing of the interference from the scale membranes. And the racial reflection is from the microstructure of the scales. The scale is standing on the membranes with different tilting angles, so they can reflection at the reflection. So besides of the structure color, we also found the butterfly also have the superhydrophobicity. So we hope to use these two properties combined together to use the cross wrinkles or use a weak interface to make to play with the structures, structure colors. One big problem of the structure color is the angle independent. Although the structure color have a strong intensity, high purity, and UV durable, but the angle independent limited its application. So they couldn't use as a normal dye or pigment because the color will be changed. So we hope we can produce a pigment-like structure colors. So we can use structure color to painting, to writing, and the color will be maintained for a long time. Normally, the people also to control the order of colloidal assembly to make uniform colors, uniform structure colors, like people just make a colloidal crystalline or disperse the narrow particle in the solution or polymer to destroy the order of the colloids. So we want to make the cozy amorphous structure also can make uniform structure colors. One method we just want to control the solvent evaporation because when the droplets because the colloidal was assembling, they will be aggregates at the edge, make coffee rings or make some balls. So if we fast evaporation the solvent, they can suppress the self-assemble process. So the uniform structure can be made. So this one is all made by the different size of silica nanoparticle. We just spring, use the ethanol as a solvent, so we can make a uniform structure colors. We can find that at different angles, the color are all the same. Because that spraying method also depends on the tools. So we hope we can make a uniform structure color use different methods like painting or writing. So now we just found one method. We make a small particle on the silica nanoparticles. So this one we call the pumpy nanoparticle. When we drop different kinds of nanoparticle on the different substrate, we can find the silica nanoparticle. They can show the such color, but the coffee ring effect is very strong. But the pumpy particles, they can make a uniform colors and uniform structures. Because the particle, the morphology of the particle is a change, and the self-assemble behavior also is a change. We can see the spherical particle, we can see the container line is moving, and the pumpy particles, the container is fixing, and they suddenly just dry together. This way, they just make the coating is very uniform. So we can use this ink as the ink to like writing or painting or stacking, generate uniform structure colors. And this research was reported by the book of the writing of the bio design. Another question is that when we make the uniform structure colors, so we found that if with the water, drop of water on the surface, water can be infiltrated in the pores. So the structure color is disappeared. So can we make a structure color with a superhydrophobicity, similar like the morpho butterfly? So to solve this problem, we just modify the silicon nanoparticle with the fluorinated saline. So then coating on the surface, we can find we can generate a superhydrophobic surface with structure colors. And also, besides the spherical nanoparticle, we also use the strained nanoparticle. So this special nanoparticle, we can make like a fractal-like structure with very high porosity, and they can generate very high contact angle and very low sliding angle for oil and water. So for hexane decaying, they also can make more than 150-degree oil contact angle. So if we coat it on different substrate like concrete, fabric, even electronics, they also can work underwater. Even though we just coat on the fin of the air condition, they can have a faster reducing the ice. The second part, we use the wrinkle to make a structure color and the superhydrophobicity. So wrinkle is a very common mechanical phenomenon in the nature. So this phenomenon need two layers. One is the rigid layer and one is the soft layer. Because of their modulus different under the deformation, the surface will be instability. They can generate wrinkles. If the wrinkle is ordered, they also can generate structure colors. However, this one is similar like the grating. The structure, the color also is angle independent, and it's similar like the thin film. We also found that the color is angle dependent. So can we combine them together to make uniform colors? So here we use the mechanism. So first we use to generate the structure color by the thin films. They can interference from the two surface of the thin films, and we can make a larger wrinkles. This wrinkle have the scattering properties. So combine the thin film interference and the wrinkle scattering, they can generate a uniform colors. So in this research, we use the UV curable polymer coating on the surface to control the thickness of the coating. We can generate different colors, and under the UV cooling and heating, because of the modulus gradient modulus and the deformation thermal expansion of the substrate, the coating can spontaneously generate wrinkles. So we tested the view angle. We found if the surface, flattened surface, the view angle only 2 degrees, and when the surface is wrinkled, the view angle can be increased to 45 degrees. Here is the simulation results, and this one is the measurement. Because of the wrinkle also is dynamic, have a dynamic properties. So we use the near infrared to illuminate the surface. The surface can absorb light, and the wrinkle will be disappear. So at this other angle, we can see the color also will be disappear. So this one shows the view angle under the near IR radiation. So please see the video. So near is on, the color disappear, and the structure also disappear. When the near is off, the structure will be come back, and we also can see the colors. Otherwise, we just make some wrinkles on the fibers, because on the fibers they have many periodic structures. So this one is they have a periodic structure at the circular direction, and this one is at the radiant direction. However, there's no periodic structure can be made on the across the axis direction. So to generate this earthworm-like structure, we just coat the PDMS precursor on the PET fiber and use plasma to treat it on the surface. So by control the intensity and the electro energy of the plasma, we successfully to make the wrinkle-like structure on the fibers. Because the low surface energy of the PDMS and the highly roughness of the nanostructure, the fabric can be easy to reach the super hydrophobic. We can see the treated fabric can repel water. The reason why the coating can form the wrinkles on the fiber, it's because of the plasma can gradient cross-link the PDMS precursor. So they can generate 3 layers, like a stiff layer, lenient layer, and the rigid support substrate. So here is the nano indent measurement. We also can find the modulus is gradient decrease. So because of the thermal expansion and the gradient modulus, the PDMS was instability. They can generate wrinkles. We also test the robustness of the fabric we found the fabric can bear very high laundering cycles and rubbing cycles. The results was almost the best of the fluorine-free coating. The reason, this reason could be benefited from the two parts. One is the wrinkle. So wrinkle can be flattened and recover to. Another one is the gradient membrane. So from the simulation, we can find if the coating is gradient, they can the stress is not very high. It is the lowest than the uniform coating, and the even the coating modules is high on the lower modules. So the benefit of these two parts, the fabric can be very high laundering cycles. And also, due to this special structure, this work also is reported and highlighted by the science. The last part, we want to introduce the weak interface, induce the dynamic scattering. Similar like the octopus, their skin can be stretched, their cells can be stretched to show transparent and colors. So we want to mimicking this phenomena. First, some research also use the micro pattern. We also can find the cracker the optical residue still exists. So can we make the coating totally transparent? Another one is can this one make highly sensitivity coatings, sensitivity smart membranes? So to solve the first problem, we think if we couldn't see the optical residue, we can reducing the size. If the size is lower than the 100 nanometer, so the scattering is out of our eye visible range, so we couldn't see it. So here, our strategy is to use the silica and the PDMS to make a composite system. To design this membrane, so we found silica and PDMS. They have the similar reflective index. So put them together, it's a totally transparent. So, and the mechanical Young's module is totally different. So for example, silica is like 60 GPa, and PDMS is less than 1 megapascal. So when we stretch them, the interface, a new interface will be generated. So this voice will be caused like a PDMS vacuum and the silica vacuum. They have a new interface, light scattering interface. So they can form a transparent change. So here is the code membrane. When we prepare this one, it's totally transparent. When we stretch them, it's opaque. And due to the narrow voice, the transparent can be change will be very high. It's like 40% change, and the initial transparency will be higher than 90%. And also, one thing is we found this one, its opacity will be changed at 40. It's not, the sensitivity is not very good. Only the structure is higher than the 40%. We can see only can see the color change. So we want to make we hope to make a more sensitive smarter membrane. Now, recently, we just induce a weak interface between the PDMS and the silica nanoparticle. So here we use like a dye, Sudan and blue ink. So we for this two ink induced interface, we found actually the silica and between the interfacial energy between silica and the dye on the PDMS dye is high, but the interfacial energy between the dye and dye is very low. So this one can be cause the low weak interface. We also found that when we coat on the surface, the micro beads is easier to generate a crack at a lower strain. So here we use the silicon nanoparticle and use two steps. One is a spray on the surface, and then spray the dye solution and cooling the surface and cast the and peel the membrane. From the video, we can find the top one is a normal silica PDMS membrane. The bottom one is silica PDMS with dye. So we can find if we introduce the dye, it's easy to cause opacity. When we test the transparent change versus strain. So it found that when we induce the dye, the transparency will be low a little bit, but the sensitivity was increased very high. So this one could be used for the smart membrane, also like a sensor for the mechanical deformation. Okay, here is the summary. So we use the chloride assembly for structure color and superhydrophobicity. Another one is we make wrinkled thin films to make a uniform structure color and superhydrophobicity. So third part, we induce the weak interface to cause the dynamic like scattering. Okay, at last, we want to thank the Professor Shi Yang, Xiaoming Yang, Xu Songjiang, and Ying Guo. So they support us for the research and our group members, and also the government to support our research. So if anyone have interesting about research, you can contact me by this email. Thanks.